What's up, nerds? We have here a two-dimensional kinematics example. We have a few questions to answer about a football, which is kicked at 24 meters per second at an angle of 30 degrees above horizontal. So what does that mean? It means if someone were to kick the football in a perfectly flat line level with the ground, that would be an angle of 0 degrees above horizontal. But that's not what happened. We kicked the football, or the football was kicked at an angle of 30 degrees above horizontal. Now, what is the football going to do? It's going to go back down and land on the ground at some later distance downfield. So it's going to increase its height to a peak and then come back down to the same height that it started at. So the first question is, what are the vertical and horizontal components of the football's initial velocity? And we have a velocity of 24 meters per second, an angle of 30 degrees, and we are asked to find, let's use some colors here. We are asked to find Vx, and we are asked to find Vy initial. Notice I didn't say Vx initial because Vx doesn't change. Vy changes due to gravity, so after the initial y velocity it will be changing, but the x will not. So the x component is adjacent to 30 degrees because it's touching the 30 in this little corner here. The hypotenuse and the x side are touching the 30 degrees, making it adjacent. So we can say that, here, let's work over here. Cosine of 30, according to Sakatoa, cosine is opposite over hypotenuse. Sorry, adjacent over hypotenuse. Cosine is adjacent over hypotenuse. So we have Vx over 24. Now I can multiply both sides by 24, and I get Vx equals 24 cos 30, which is equal to 20.8 meters per second. We can do the same thing with y, except the y side is opposite to the 30 degrees, and Sakatoa says that sine is opposite over hypotenuse. And therefore, if I multiply both sides by 24, I will get Vy equals 24 sine 30, which is equal to 12. Okay, so we have here our Vy and our Vx. All right. Now the next question says, how long is the ball in the air? Now, for a two-dimensional question such as this, where the ball is moving horizontally and vertically, I like to start by separating my variables. And we want to make sure to only calculate using the x variables or the y variables in one formula. You can use x in a formula or y in a formula, but not both. The only thing that goes on both sides is time, which we don't have yet. So for example, Vx is 20.8, Vy is 12, and what else do we know here? We know acceleration in the y dimension is negative 9.8. That affects only the vertical dimension, not the horizontal dimension. And we know for a problem when the ball comes back down to the same height, if the y velocity here, the vertical velocity component here is 12, then on the other side at the same height, the vertical y velocity will be negative 12 when it comes back down to that same height. So I should say Vy not there for the initial velocity. Vy final will be negative 12. We can also say that d is 0 meters, dy is 0 meters, because when we go up and then down, we're coming back to the same height, which means that our y displacement is 0. We will have x displacement, which is this way, but if we went up and then down, we have no y displacement. So how long is the ball in the air? We can use this formula v equals v naught plus at to solve that. And we need to solve for time before we plug in our value. So I can subtract v naught from both sides, leaving me with v minus v naught equals at. And then I can divide both sides by a, giving me t equals v minus v naught over a. And the final velocity is 12. The initial velocity, final velocity is negative 12, minus the initial velocity, which is 12, divided by the acceleration, which is negative 9.8. The negatives will cancel, and I get a time of 2.45 seconds. Part C here says, how far away will the ball land? Well, looking at my table, I can bring the time to the x side here. Time can go in x and y, because it is a scalar. It doesn't mind if it goes from x to y. Nothing else can go from x to y. Velocity, acceleration, displacement must stay separate, but time can go on both sides. So, looking at my table, I'm going to use this formula to solve for x displacement. We always use this formula in the x dimension because it doesn't have acceleration. So this says v velocity is displacement over time. In this case, I've added an x because I have my x velocity and my x displacement. I multiply both sides by t, leaving me with dx equals vxt equals 20.8 multiplied by 2.45 seconds, giving me a displacement of 51 meters. Part D says, to what maximum height will the ball rise? So we're interested here only in the first half of the problem. I'm going to remake my table because it's off the page and because we need to update a few things. First of all, Vx is still 20.8. Vy initial is still 12. I can no longer say Vy final is negative 12 though, because we're not going back down to the same height that we started at. I can, however, say Vy final is 0 at the highest point, because I'm only moving to the side here, I'm not moving up or down. So I can say my final Vy is 0. I can say Ay is negative 9.8 meters per second, and I will write down here that I'm looking for a D. I can pretend that fit into my table. Now, using only the y things, remember we use only x or only y, I need to find displacement. So I think of a formula where I look at my formula sheet and I see the formula that has these four things is v squared equals v naught squared plus 2ad. Final velocity is 0, so I can cross that out. I'm going to subtract v naught squared from both sides, leaving me with, so I'll have plus v naught squared minus v naught squared on the right. It will cancel out. I'll get negative v naught squared equals 2ad. I will divide by 2a on both sides, leaving me with d equals negative 12 squared over 2, negative 9.8. And that gives me a y displacement of 7.35 meters. So the maximum height that the ball reaches is 7.35 meters above the ground before it starts returning back to the field. Last question, with what total velocity will the ball land? Maybe, if you're tricky, you can think of the answer to this before we calculate it, but just in case, let's calculate it, in case you haven't thought of the answer. So we leave at 30 degrees at 24 meters per second. That includes an x velocity of 20.8 and a y velocity of 12. Now let's think when we go to the other side. Sorry, this is not a very symmetrical arc. That's slightly better, I guess. When we go to the other side, we will have here our final velocity vector. This is what the question is asking for, v final. Now our final velocity vector, much like our initial velocity vector, this is our initial velocity. The initial is 24. So our final velocity is the same in that it has an x component and a y component. I'll call them Vx and Vy final because I don't say Vx final because Vx hasn't changed. And because it hasn't changed, it's still 20.8 meters per second. Vy final, if we reach the same height, we've already discussed, is negative 12 because it was shot upwards with a vertical velocity of positive 12. It comes back down to Earth at negative 12. Now you can see the components are the same on both sides. If we find Vf by saying v squared, or Vf squared equals root 20.8 squared plus negative 12 squared, we will find that it is, of course, 24 meters per second, the same as the initial velocity. If we find the angle here below horizontal, we will have to do tan inverse because tan is opposite over adjacent. We will do 12 over 20.8, and we will find the angle below horizontal is 30 degrees, the same as the angle above horizontal when we started. So the answer to part E is that the final velocity is 24 meters per second at 30 degrees below horizontal. Now, this may have seemed a little bit useless that we calculated the same value that is symmetrical on the other side, but if we were to throw a football from, let's say, we were standing up in the bleachers and we threw a football off to a lower height and we wanted to find this final velocity, well, then the process that we've practiced here of using Pythagoras and tangent to find the final velocity, it would be useful in this case because we wouldn't know what the final velocity value is. We would have to find the x component and we would have to find the y component to find the total velocity vector. So this is useful in other situations, not just on situations where the object falls to the same height. All right, thanks for listening. Have a good one.